Wait, why can't I hear you guys? There you go. Okay, so Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning. So let me see. Just do that. Look at my screen. Awesome. Okay, so welcome back GIS1003 with me. Last week you had your session with Dr. Mas, okay, Dr. Mas Mira. So today what we're going to do, as per last week, so last week we did our lecture first. I did a little bit of introduction, and then we went through the lecture notes, and then we did a little bit of tutorial. Okay, but today I'm going to change it a little bit. Since there's no more introduction, or the introduction will be very, very quick. So what we're going to do today is we will start off with just a few slides of introduction, and then we're going to play poll everywhere. Okay, so just be ready, okay, with your devices or your browsers and whatnot. And then once we have finished with poll everywhere, we will go into today's lecture notes. We should be able to cover it very, very quickly because there's not much chemistry, like detailed chemistry in there. And then we will end our session with another poll everywhere, which is related to lecture number 2, okay, which is related to this lecture. All right. So again, this is just a recap about the learning outcomes. So basically what we've covered last week is for you guys to be able to explain the basics about chemistry. So looking at atoms, elements, mixtures, compounds, and so on. Okay, so I'm hoping that at least by today, once we end our first summary, okay, you should be able to grasp this concept very, very strongly. Okay, and then today we're going to look at a little bit, but still related to number 1. Okay, we're going to look at identify the connection between molecules. So in particular, we're going to look at air molecules, and then the gases inside air. We're going to look at water a little bit, and then finally we're going to look at ammonia, which is very, very quick. Okay, and then we're going to skip to that one later on. Okay, so topic for today, we're going to look at air, water, and ammonia, and then in 2 weeks' time, we're going to look at smoke, pollution, acid rain, and then perhaps we will include a little bit on hydrocarbon. Okay, it depends on the lecture notes, because this is my first time giving you guys a lecture for this subject per se. So I need to do a little bit of preparation, revising the notes to make sure that it goes up into your level, since you guys are not from chemistry. Okay, so gonna go and do that next week. So for today, you're gonna just do a little bit of that, okay, and then we will focus on air, water, and ammonia. Okay, now last week I mentioned that your final exam is not yet ready. I mean, in the sense that I have yet to decide whether to do a final exam or an alternative assessment or whatever it may be. Yesterday or probably last Friday, the lecturers have finally received the instruction from the central university, and we now have a little bit more detail on what we can do, what we cannot do, and what should include, and so on. Therefore, I have decided to do an alternative assessment. Okay, so you'll be given an assignment, and that will be given on week 11 here. Okay, so on week 11, I will give you guys the instruction for your assignment. I hope that none of the other subjects have given you the same assignment, and so what I mean here, general instruction is basically not the final ones yet. So it's just a basic instruction on what can you expect. Okay, it will be an open book type assessment. You can and then you will have about 2 weeks to complete the assignment. Okay, so it's very relaxing, and there's a lot of information digging needs to take place. Okay, so instead of memorizing all the lecture notes and whatnot, what you need to do is basically you need to understand a little bit. You need to understand what the lecture is all about, and then apply it in your assignment. Okay, so instead of memorizing and whatnot, so it will be an open book assignment, so don't worry. And then on week 7, we will still do our quiz. Okay, so we normally have 2 hours of lecture. So what we will do is on the first hour, we will do the quiz. Okay, and then depending on whether I was able to catch up with the lecture notes or not, then on the second hour, we will either discuss about the quiz, or we will continue our lecture. Okay, so either or. Normally, I would like to discuss because at least you will learn about, if you got it wrong, then you know why you got it wrong, instead of just getting a grade, whether you get an A, B, C, a D, or whatnot. Okay, so I'll try and include that element within week 7, but there's no promises, because it all depends on whether we will able to catch up with the lectures or not. Okay. All right. So moving back to module number 1, introduction. So what we do now is we will start off with poll everywhere. So I hope that you guys can open your poll everywhere and answer these questions. Okay. So basically, if you notice, it says there L1, Q4, because I've already prepared all the questions last week, but unfortunately we did not have enough time to actually do it in class. So we're gonna do it today. Okay, so can you open up your poll everywhere? Again, if you open polleverywhere.com, okay, or pollf.com / write up Hadi Fuad 049, okay, to join in to participate. So pollf.com and then / this name. Okay, so all the questions are anonymous, so you don't have to worry whether you might got it wrong or whatnot. This is just for you to kind of like practice or look at your understanding. Okay, and pretty much gives me a little bit of feedback on whether I need to look it in very detail or not. Okay. All right, so the first question, it says, what is the name of this bond, the hash line? So if you look at the hash line, not the dotted line, the dotted line is normally like that. Okay, so it's a hash line. So what is the name of that particular bond? Let's see, how many do we have so far? Oh, you guys keep on changing your answers. Let's see. We have approximately 13 hydrogen for dispersion, 70-ish% dipole, and about 8% intermolecular. None of you selected none of the above. Okay. All right. So 1, 2. Final chance to change your answer. 1, 2, 3. Okay, I'm gonna lock it. Okay, so the most accurate answer is dipole. Okay, so this is the most accurate answer. Okay, why dispersion is wrong? Dispersion normally focuses on structures which are non-polar. Okay, what do I mean by non-polar? If you look at the structure itself, so one example, one key indicator given is carbon monoxide. Okay, carbon monoxide is like that. Okay, if you look at the structure in very detail, there's actually 3 lines. over there. There's 3 lines. If you can see that, I cannot draw anything here because of the module. Okay, so the structure is like this: C with a triple bond, O. In this case, probably is the other way around. O is over this side, C is over that side. Okay, so why do I draw it O on the left hand side? Is because O is more electronegative. Okay, and C is electropositive, or C has a positive charge, or delta positive. It's not a pure positive, it's more kind of like temporary, or that's what we call as delta, temporary positive charge, while oxygen has a more negative charge or temporary negative charge. Therefore, we put it as delta sign. So delta minus and delta plus. That indicates a temporary charge. It's not a full charge. A full charge for chemistry, we normally draw it like that. Okay, or a plus or a minus with a circle. Okay, so say for example, if I were to draw sodium chloride, so sodium chloride, which is salt, okay, I'll draw it like that, and A plus and Cl minus. So this indicates full charge, while delta indicates partial charge, so or dipole. Okay, so in this case, if you were to draw it, okay, the big bulb, what can it? Okay. So the big bulb is actually an electron cloud. Okay, so what we have here is a very big electron cloud on the oxygen and a small electron cloud on the carbon. Okay, so it draws like that. So if you consider, and then the second one, I'll just draw it here, C and then triple bond O. Again, small electron cloud, big electron cloud. Okay, so the question asks about this connection or this bond. And because carbon monoxide is a dipole, okay, because of the presence of the delta charge. So delta charge is based on the electron cloud, okay, the drawings that I've drawn. So the connection between these two, delta negative and delta positive, are dipole. Okay, dispersion, if I were to draw, where can I find more space? If I were to draw, say, carbon dioxide, okay, with another carbon dioxide, okay, because we have an opposite charge of oxygen, so the electron cloud should go something like that. Okay, a little bit big in the O, slightly smaller in C, and then a little bit in O. Okay, so that one, then you might have an interaction between here or here, and depending on the whole molecule, if you have another CO2 over here, then you may have a dispersion force. Okay, but the more accurate answer for this particular image is a dipole. Okay, let's move to the next one. Which of these is not an element? Okay, you have carbon, you have aluminum, you have steel, you have sulfur, and we have bromine. So which of these is not an element? Okay, so we have 80% steel, 7% sulfur, 13% bromine. Oops, going down. We currently have no carbon and aluminum. We have carbon, aluminum, steel, sulfur, and bromine. Which of these? I will give you guys 30 more seconds. So which of these is not an element? Okay, so carbon, aluminum, steel, sulfur, and bromine. Okay, 5 more seconds. 4, 3, 2, and 1. I cannot see anything. Okay, so oh wow, So the correct answer is, yay, 100% correct. So it's steel. Okay. So carbon is an element. If you remember the definition of an element is everything on the periodic table. Okay. Remember the kind of like the table with all these fancy names and whatnot. Okay, so those are all elements. So we have carbon, we have aluminium, we have sulfur, and we have bromine. Okay, steel is not an element because steel is a mix. Yeah, it's a compound. Okay, it's a mix of, what is it, iron and a little bit of carbon. You have a little bit of oxygen at a varying degree. Okay, so then that's when you get steel. Okay, good, 100%. Next one, oops. The next one. The molecule paracetamol belongs to the compound category. Okay, so true or false, very simple ones. So this is a picture of paracetamol. Okay, so for those who might know or might not know, paracetamol is what we when we were a kid, or probably when you were a kid, you normally or you might have consumed Panadol. Okay, Panadol. Okay, so especially if you have a fever, if you have a headache, so you normally consume Panadol. So the active ingredient in Panadol is this guy. Okay, so this is what we call as paracetamol. Of course, there's a chemistry name, but for you guys, it's enough to know that it is called as paracetamol. Okay, so this is the active ingredient. Now, do you consider this molecule belonging to the compound category? I'll give you guys 15 more seconds. Let's see. So true or false? Paracetamol is a compound. 5, 4, 3, 2, 1. The correct answer is ding, true. Well done again. Yay. There's no clap button, like Teams, but anyhow. Okay, next one. The smallest stable unit of particle is known as one atom, nucleus, proton, electron, or none of the above. The smallest stable unit of particle. So again, these are all based on lecture 1. Okay, we haven't got to lecture number 2. So all lecture 1. Okay. Smallest stable unit of particle is known as atom, nucleus, proton, electron, or none of the above. Oh, interesting answers. Interesting distribution. Let's see how many have answered this. Fresh. I have 22 responses. Anyone else wants to join in? Anyone else wants to join in? There's 40 of you, or not 40, about 37. It's only half. What happened to the half? If you want to join in, just go to there, polf.com/hadifuad049. You can do it on your browser or on your mobile browser. You know, there's multiple options. You can just join in. Okay. All right, last one. I'm gonna refresh. I have 23. Anyone else joining in? Oh, half of the class are doing something else. I'm sad. Never mind. I hope that you guys who participate will score better than them. Okay. All right, I'm gonna stop here now. Okay, the smallest stable unit of particle is known as. Why does it work? Hold on. Oops. I keep that one. I'll do that. Atom. Okay, so why is the other answers wrong? One thing, nucleus is the center of an atom. Okay, nucleus doesn't stand on its own. So you know that it exists, but it doesn't stand on its own. Okay, similarly, nucleus contains protons and neutrons. So you cannot separate protons and neutrons and then just leave it as it is. Okay, you need to, if you want to extract it out, you need to react it with something else so that towards the end of the day, it will form again an atom. Okay, similarly, electrons is the same. It does not stand on its own. It's always attached to something else. At least for now, at least for the current technology that we have, all of the other three always needs to have something that towards the end of the day, it goes back into an atom. Okay, so atom is the stable unit of particle. So if, say, for example, the question is changed to what is the smallest unit of particle, then the answer can be if there's so if you compare within those three, nucleus, proton, and electron, then the correct answer is electron. Okay, so electron is the smallest among all the four answers. But if, say, I put in quartz or what's the other one? Quartz particles, then quartz will be the correct answer. Okay, so if you can't recall about the differences, then go back and revise lecture number 1. Number 8. Name one item containing the element carbon. So this is very easy. Just name something that contains an element carbon. Very easy. Okay, so you have carbon dioxide, which is the easiest answer. You have carbon monoxide. You have diamond. Yep, that's correct. Oleate something, I'm not sure what. Kentucky Fried Chicken, that is also correct, yes. KFC. Paracetamol, yep, we just looked at the structure of paracetamol, so that one is also correct. What else? What are alternatives? Plastics, yes, we do have carbons in plastics. So far that I've known, all plastic still contains carbon. Okay, so we have methyl something, which is correct as well. Okay, plastic drinks, still the same. Okay, still correct. Of course, chicken, if you just exclude Kentucky Fried Chicken, just consider chicken, then of course chicken still also contains carbon. Nobody says human, nobody says yourself. So there's a lot of examples of materials that contains carbon. Okay, so pretty much every single thing, paper, for example, your table, if it's made of either plastic or wood, it still contains carbon. Okay, the air, so we have part of it has carbon. Of course, not 100%, but part of it. You have what else? Mask. Okay, the mask that you guys, everyone wears, also contains carbon. Okay, so I'm pretty sure everybody knows about this. Okay, so thank you for answering. Let's move to the next one. All right, so the next one, carbon dioxide is a what molecule? Carbon dioxide is a what molecule? Is it a charged molecule, polar molecule, non-polar molecule, ionic molecule, or none of the above? So this is the structure of carbon dioxide. So that is how it looks like. Okay, so I'll give you guys about 30 more seconds. So yeah, just quickly, for those who still wants to participate, the link address is up there, polf.com/hadi4049. Okay, and then the question should pop up on your mobile. As long as you get you have a good internet connection, it should be rather quick. Okay, because there's no picture, it's just words. So yeah, carbon dioxide is a what molecule? Is it a charged molecule, a polar molecule, a non-polar molecule, ionic molecule, or none of the above? Let's see again. We have 22 responses. Anyone else wants to join in? Please join in. We still have a few more questions to do. Okay, right. I'll just stop it there for now. And the correct answer is, why doesn't it change? Ding, 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 ding. Oh, oops. Unfortunately, I'm not able to show you guys the correct answer. The correct answer is non-polar. Okay, so again, this question reflects back to the previous questions, one of the previous questions, okay, when we are talking about carbon monoxide. Okay, so carbon monoxide is a polar because if you just consider C double bond, triple bond with O, O has a bigger electron cloud, bigger, higher electronegativity compared to carbon. Okay, because of that, you get a partial negative on the oxygen and partial positive on the carbon. Okay, so that is a case of carbon monoxide. But now when we are talking about carbon dioxide, so that's the structure. Again, if you consider that one as delta plus, okay, and then oxygen as delta minus in both direction. So what are the differentiating factors between a polar or non-polar molecule? So basically, if you're looking at polar and non-polar, right, and perhaps charge, okay. So the main differences is, if say it's like if you're engineering, okay, if you're thinking about two opposite direction forces or charges or something that moves in the opposite direction, okay, so you can consider this direction going into that way, that one is going that way. Okay, again, because when we are talking about electronegativity, what it means is that the atom likes to have more electrons. Okay, so that's why you can see the electron cloud for oxygen is way bigger than in carbon. Okay, because all the electrons like to move towards this direction. So it moves from the delta positive charge to a delta negative. Okay, because delta negative means that it's partial, meaning that there's a little bit more electron in the oxygen compared to carbon. Okay, but if you consider the carbon dioxide, the situation in carbon dioxide, because now you have a pulling direction on both left and right, therefore there's no net, what's the keyword, net electronegativity. Okay, so the keyword here is net. So you have it pulling to both direction, so there's actually no net. When there's no net, then it becomes non-polar. Okay, so when it's no net, it becomes non-polar. So 92% of you guys got it right. So why is it not charged? Because for a charged molecule, it needs to be separated altogether. Okay, so say for example, sodium chloride, in its native form, in a table salt form. Okay, so the salt that you do if you're cooking, or if you have seen table salt in you know, supermarkets and whatnot, so it's white in color. So in that particular form, the structure is like this. Okay, so it's kind of like compact to one another. But once you dissolve it in water, it will form a charge. Okay, so the charge doesn't really exist, so to say. It's there, but it doesn't really exist unless if you put it in water. So when you do in writing, okay, you put sodium chloride when it's a solid form as that, say NaCl with S, you don't write it like this if it's a solid. If you dissolve it in a liquid, in a solution, or what we call is as aqueous. So aqueous, aqua means just water. So when you dissolve sodium chloride in water, it forms Na plus and Cl minus. Okay, so those are the differences. So when it forms like this, then you can say that it is charged. Okay, if you look at the structure of carbon dioxide, there's no full charge at all. So you cannot break this bond. Okay, so this cannot be broken. It cannot be O minus and then C plus and then O minus. It doesn't work that way. So if say by any chance that it works, okay, you can form an O minus and then C plus and then another O minus, this molecule will no longer be a carbon dioxide. Okay, carbon dioxide, again, if you look at the definition of a molecule, it needs to be bonded. Okay, it needs to be bonded to one another. It cannot be separated. So carbon dioxide, as that structure, is a non-polar molecule. And the last one before we go into our lecture for today, okay, how does hydrogen bond or H bond forms? So we have a few options here. First one, when an atom shares electron with another, then you form hydrogen bond. So when a polar molecule is close proximity to one another polar molecule, you form hydrogen bond. Or when a non-polar molecule has a close proximity with another non-polar molecule, you form hydrogen bond. Or the last one, when you have, second last one, when polar hydrogen delta plus is bonded with electronegative delta minus atoms, meet another electronegative atom, or D, none of the above. Okay, so what do you guys think would be the most accurate answer? I have 11 responses for now. The answer keeps on changing. Okay, so how does a hydrogen bond forms? So give you guys another, say, 15 seconds. Okay, 15 more seconds, then we'll start the discussion, and once it's done, then we'll go into lecture number 2. Okay, meanwhile, I want to drink. Okay. Oh, now we get 35 responses. Good. Awesome. Okay, so I'm gonna stop in 3, 2, 1. All right, so these are your answers. So 8% says when a polar molecule is close proximity with another polar molecule. 17 when a polar molecule has close proximity with another non-polar molecule. And then D is when polar hydrogen, okay, is bonded with electronegative delta minus atom meets another electronegative. Now, you will look at one by one. So the first one, if the answer is number 1, when an atom shares electron with another atom, then of course that one is wrong, because that is the definition of a covalent bond. Okay, so remember, for example, say hydrogen, it has one electron, it shares with another hydrogen that also have one electron. So in this case, you're going to write it as H-H, and therefore this is covalent bond. This is not hydrogen bond. So nobody selected that, which is great. Awesome. Second one, when a polar molecule is close proximity with another polar molecule. Now, this one seems correct, right? But again, if you go back and try and recall, what is another example of a polar molecule? Okay, we've covered it in the last few slides, last few questions. One good example of a polar molecule is carbon monoxide. Okay, carbon monoxide is a polar molecule, but does it form a hydrogen bond? From the previous question, the answer is no. Okay, so this one forms a dipole-dipole. Okay, so the answer for number 2 is inaccurate. Okay, it doesn't mean that it's wrong, it is inaccurate. Okay, number 3, because towards the end of the day, the question, the principle that I want to ask is which one of these is the most accurate. Okay, so number 3, when a non-polar molecule has close proximity with another non-polar molecule, then of course it is wrong, because that one is definition of a dispersion force. Okay, so hydrogen bond needs to have a polar molecule. Okay, it must be, there must be a polar molecule, and that polar molecule must come from hydrogen. So hydrogen must be there, therefore the name hydrogen bond. Okay, so as simple as that. A hydrogen bond needs to have a name hydrogen. So say for example, if you have water molecule, which is the easiest, you have H and then you have O and then another H. Okay, so you have hydrogen there. The hydrogen is connected to electronegative atom. As we mentioned previously, oxygen has a delta negative charge. Therefore, hydrogen will have a delta positive charge. Okay, so both hydrogens will have delta positive charges. So if you have two water molecules, for example, like this, so you can get again delta positive, delta negative, delta positive. So you have this. Okay, polar hydrogen is bonded, so this is what we call as bonded. Okay, with electronegative atom, which is the oxygen over here. Okay, meets another electronegative atom, so it meets another electronegative atom, which is oxygen from another water molecule. So this is hydrogen bond. Okay, all right. So hopefully it covers a little bit on lecture number 1. Okay, that is all. So this is just a recap. I will just do a very quick summary. So this is what I mentioned previously. You should be able to understand and differentiate the following: atoms, elements, molecule, compounds, mixtures, covalent, dipole-dipole dispersion, hydrogen bonds, and organic and inorganic materials. Okay, so very quick revision. What is an atom? The smallest unit of a matter. Okay, again, I just put it there in general, because if you want to go in very detail, then the smallest unit, the smallest stable unit of matter or particle. Okay, matter or particle. Elements, the purest or simplest form of substance that can be found on Earth. For example, oxygen, carbon. So anything that is listed in the periodic table. Okay, so you have many elements over here. We still have, people are still discovering about elements. Now, if I'm not mistaken, there's a third row, if I'm not mistaken, or probably there's some rearrangement on the elements that are currently being discovered. Okay, so molecule, a group of 2 or more atoms that forms an identifiable unit of pure substance. For example, oxygen makes oxygen gas, O2, CH4 makes methane gas, C6H12O6 makes a glucose. Okay, so a glucose, even though there's more than 2 atoms, by definition, it is still a molecule. Okay, because it says here 2 or more. Compounds, on the other hand, are substances made up of different elements. So you have elements from here. So in its purest form, okay, CH4 can be both compound and a molecule. Okay, so compound and molecule is not something that you normally compare. Okay, so you normally compare between compound and mixtures. Okay, if you are referring to a single unit, then it is a molecule. So if you have one glucose, then normally you say glucose molecule. But if you say multiples unit of glucose molecule, you can say it's a compound. Okay, and last one, mixture, is a mix of compounds. So you have glucose, and then you mix. You take sugar from your kitchen cabinet. You take salt from your also kitchen cabinet. You mix them together. Now you have a mixture. As simple as that. Okay. And then type of forces, you have covalent bond, the strongest bond connecting two molecule together. For example, oxygen. If you just draw oxygen like that, okay, so you have 1, 2 over there, 3, 4, 5, 6. Okay, so oxygen have 6 electron valence. Similarly, because it's O2, then you have another one. Okay, and because electron wants to have at least, normally they will have about 8 electron valence. So to consider, to account for 8 number of electrons, then these two will share with one another. Therefore, for oxygen number 1, you will have 2, 4, 6, and 8. And similarly, for oxygen number 2, you have 2, 4, 6, and 8. Okay, so now both oxygen has an 8 electron valence. And similarly, they are sharing 2 electrons between one another. Therefore, you have 2 bonds. So therefore, when you draw an oxygen, you'll draw it as a double bond like that. Okay, because each bond represents one electron being shared between 2 atoms. Okay, next one, dipole forces. It's a weaker than covalent but strong in large molecule. So a smaller example is just simply HCl. So you can see on the right hand side, you have chloride, which has a slight delta negative, and hydrogen ions or hydrogen atoms has a delta positive. So therefore, if you have, so you can see that there is a polar, a net movement, or net charge movement, or a polarity. So similarly, for that one, you have a polarity. Therefore, you can get a dipole or polar dipole attraction or forces. Okay, between the 2 atoms. If you just consider between one atom, then there is no dipole forces. So dipole forces are intramolecular forces. So it's forces between 2 or more different molecules. Okay. Next one, dispersion force, even weaker than dipole, but can be strong in large molecule. So what it means is in a singular state, it doesn't have any polarity, or polarity is net polarity is 0. So a good example that we've looked at before is carbon dioxide. So on its own, the net is 0. Okay, so the net movement or the net pulling is 0. But if you have 2 of them in a close proximity to one another, depending on the orientation, so it might induce some changes in the polarity. Therefore, you can get an induced polar, and therefore you consider it as a dispersion force. Okay, so this is just a recap. And then last one, hydrogen bond. It's the same as what the question that we completed just now. So you need to have a polar hydrogen connected to one of these atoms, electronegative atoms, and in a close proximity with another electronegative atoms. Okay, so a good example again is water molecule. All right. And last one, just a brief definition between organic and inorganic compound. So organic compound is basically or generally anything that contains carbon and hydrogen. That's very typical. While inorganic, anything other than organic. So it's a very quick definition. So for example, if you're considering palladium metals, okay, so for those who are in engineering, if you consider metals, or even if you're not in engineering, you have steel, for example. If you have a car key, okay, not kaki, not feet, but a car key, okay, so it is made of metals, elements, a mixture of elements, metals, and so on and so forth. Okay, if it's in a pure state, aluminium, so it is inorganic material. Okay, but in case if say the keys that you made is made up of wood, for example, then the key is an organic matter. Okay, so inorganic contains no carbon, organic contains carbon. But you can also have a mix of both, something that we call as organometallic, but it's not covered in this topic at all. Okay, so I'm just telling you guys that metals are normally inorganic, but you can have metal with a mix of organic materials that we call as organometallics. Okay, an organic compound, same example that we've seen last week, are cholesterol, is cholesterol. Okay, with the structure containing a lot of carbons everywhere, carbons, and a lot of hydrogens moving up and down from here as well. Okay, depending on the structure, hydrogen. All right, that is all for module 1. We have about 1 hour to go to cover module number 2. I think we should have enough time because module number 2 is very straightforward. So what are the learning objectives for today is for you guys to be able to understand simple substances, looking at a more molecular scopic of these 3 examples. Okay, so we will look at air, we will look at water, and we will look at ammonia. Okay, so we'll look at a little bit about the properties and its uses in industry. Okay, so what is an air? What makes air, the surrounding air, breathable? What is its composition? So you might wonder about that, or you might you might not care at all. Okay, but so what we're gonna cover a little bit is just for you guys to know a little bit, if you have not known so, about what is air. So air, well, before I go into the composition itself, this is just an example back in 1982. So a group of scientists from NASA, and yeah, pretty much is the old name for NASA, okay, National Aeronautical Space Agency of the US, okay, NASA. So they did an experiment on how can you determine the atmospheric composition. So composition meaning a mixture of air. So air is nothing, pretty much air is just a name. So it's a mix of a lot of gases. Okay, so this group of scientists did an experiment on how do you actually determine the composition of air using UV light. Okay, so and if you read the paper, it's actually very interesting because they are looking at aurora. So do you know dayglow and aurora? It's if you go into the north or south pole. I haven't been to any of those, of course, but if you can just Google aurora now, then you can see it's a very beautiful light effects in either north or south pole, depending on the season. Okay, and so what they are doing is they are doing an experiment on how analyzing the aurora can tell you what is the air composition. So of course, for me, it's very interesting because it's chemistry, but for you guys, I'm not sure. Okay, but this is just one example on how scientists being able to identify what is the composition of air. Because if you are not in the field, normally you might wonder, like, or you might criticize something. Say, for example, if I say in this water, it contains not just water, but something else like salts and whatnot. Do you think you will believe me? If I were nobody and I'm just gonna say, oh, it contains something that can cure cancer, for example. So of course you will not believe me because for one thing, you want to prove. Okay, so for anything that people say, normally you want to have a proof. Okay, so that's a good thing to do. Ask for proof. It doesn't mean that it's bad. It's also okay. Okay, it's okay to ask. So similarly, when we are talking about air, what do we actually breathe? Are we breathing air, or are we actually inhaling something else? So in the air, it contains roughly about 78% of nitrogen. So pretty much the bulk majority of air that we breathe in are actually nitrogen. Okay, we are actually breathing in nitrogen. But among the air, the volume of air that you breathe in, you have 21% of oxygen, and then you also inhale roughly about 1% of other gases that includes carbon dioxide, monoxide, methane, and so on and so on. There's a lot of molecules in the air. Of course, depending on where you are. So say, for example, if you are just standing next to a very big tree, or if you are standing in the middle of a forest, then this percentage might go even lower. Okay, you might get a higher percentage of oxygen, and nitrogen is more or less roughly the same, regardless of where you are. Okay, but that's the general principle. Oxygen is more abundance where you have more trees, and it doesn't mean that it gets slower, because towards the end of the day, everything balances out. So say for example, if you have a two area, okay, a two box, a fully contained airtight box, okay, and we have one hole over here and one hole over there, and in the middle of the hole you have kind of like a tunnel. Okay, so if you have 100% of oxygen over here, okay, and then you have 100% of nitrogen on the other box, okay, so if say originally it is closed, so of course when it's closed you'll get a total separation of both gases. So one is 100% oxygen, another one is 100% nitrogen. But once you open this, so what will happen is there will be an influx, there will be a mix of oxygen moving from the left to the right, and vice versa for nitrogen. And towards the end of the day, what you will get is 50% of nitrogen gas to oxygen on the left hand side, and similarly you'll get something similar on the right hand side. Okay, so this is a basic principle of chemistry. A higher concentration will move to a lower concentration. So when we consider the percentage as a concentration of gas, okay, it will always move to a lower concentration, so until it gets equal. So say for example, if you're in the middle of the forest, and then if we want to say for the sake of just number, okay, you might have 50% of oxygen in the forest, because oxygen are being produced by trees. Okay, so at one point there will be air movement, there might be some hurricane blowing the oxygen away, so towards the end of the day the values, the numbers will go down to roughly about 21%. Okay, so normally it don't go down below 19%, so it fluctuates. Of course everything fluctuates, but it will stay roughly about 20%, 20 to 21%. Okay, so what happens if oxygen number goes lower? Then if it goes lower, then it will affect humans, it will affect all the animals and so on. So if you go below, if I'm not mistaken, about 15%, you'll get like a lightheaded or small headache. Okay, so that's why sometimes the older generation says when you yawn, like, you know, when you're sleepy, you normally yawn, right? So yawning is a sign that your body lacks oxygen. Okay, so sometimes if you're yawning, especially if you're studying, okay, if you're yawning, so one, it's a sign that you are bored. Second one is a sign that your body lacks oxygen. So what you can do is you can just go up, stand, breathe in a few times, and normally you feel a bit refreshed. Okay, so that's one way you can do it. This is how you relate this subject with what you are doing in your daily life. All right, so how do scientists determine the composition? Again, if you want to read the paper that I mentioned just now, then you can just Google or type in that one in bit.ly /separate_air. Then you should be able to link and open the paper if you are interested. Okay. Otherwise, what scientists can do is actually using the process called fractional distillation of liquefied air. Okay, so this one should be a video. It's not playing. Let's see if I can play it. Unfortunately, I cannot play it here. So I'm gonna switch to my PC in a while, and hold on 1 second. Let me see. Different subject. GIS. Notes. Week number that one. Okay. This one should be a video, so I'll just play the video from my desktop instead. My screen. I'm gonna share this one. Okay, and then after this, we're gonna continue. Right. Oh, can you guys see anything? No, right? Let me see. Oh, how do I adjust this? Google Meet. Audio microphone found. Unfortunately, I cannot play this. But anyhow, I will share the link for the video with you guys, so you guys can later view it on in your own time. Okay. Unfortunately, the video is not playing on my iPad. Needs to click copy paste. Yeah, so I cannot play it, even though it's there. Hopefully, this one I can play. Okay, so this one is playable. All right, let's moving back to that one. Okay, so just have a look. This is how part of the process of a company that separates air. Okay, so say for example, have you heard about liquid nitrogen ice cream? Okay, so liquid nitrogen ice cream uses liquid nitrogen. So we have, as I mentioned, we have a lot of nitrogen gases. Okay, so liquid nitrogen is basically what this factory does. So it takes up, it cools down our air. Okay, in general, basic principle, it cools down our air into a liquid, and then it does something like this. So this is, in chemistry, this is a distillation process. So what distillation does is basically it separates molecule depending on the boiling point. So you know, say for example, if you have water, okay, if you take the tap water and then you boil it, okay, so when you want to make a hot drinks, right? So you boil it. So the boiled water, when you take from a tap water, it's roughly about 100 degrees Celsius. Okay, it boils at 100 degrees Celsius. But say, for example, you take a tap water and then you put a lot of salt in it, okay, and then you boil it. So it will no longer boil at 100 degrees Celsius because now you have sodium chloride that forms an ion with the water molecule in there. So the boiling point will go higher. So it will not boil at 100 degrees. It might boil at 110 degrees, for example. So the same principle is being done here. So if you have like a solution or water or anything, okay, in there, you can heat it up slowly in a controlled manner. So say, for example, if now you have nitrogen and oxygen, just an example, okay? So this is not true because you cannot have a liquid nitrogen and oxygen in this setup. But say, for example, you have a liquid containing nitrogen and oxygen, okay? So oxygen, which one has a higher boiling point? Now I'm not sure. I can't remember. Okay, but anyhow, say for the sake of just learning, okay, this is just a basic simple theory. Say if oxygen boils at 50 degrees Celsius and nitrogen boils at 100 degrees Celsius. Okay, an example. So when you have a mixture of nitrogen and oxygen that boils at 100 degrees and 50 degrees Celsius respectively, so when you heat it up, you can see here it says oil bath or heating mantle. So it heats up the mixture over here. So when it reaches 50 degrees Celsius, what will happen is oxygen will start to move up. Okay, it will start to move up because it heats up faster, and because temperature goes from 0 to 100 degrees. So when it reaches 50, so oxygen will start to boil or it will heat up. So it will move up. Okay, while what happened to the nitrogen? Nitrogen, because it boils at 100 degrees, it will stay. It will stay inside here. So at 50 degrees, oxygen will move up, nitrogen will stay. Okay, and at one point, you can see everything here is a closed system. So oxygen will move from here, it will move to over here. And there is what we call as a condenser. So for those who are in engineering, if you know about, or even if you're not in engineering, but you know the basic principle of how air conditioning works, you know your aircon at home, okay, how does it blow a cool air? So the principle is like this, it's the same thing, but in this case, it's slightly different in the sense that the oxygen is now hot, and then you have cold water coming in and out. So this condenser over here is cold. Okay, so what will happen is the oxygen will move over here, going to over here, and it reaches a point where it cools down. So it will form again the original liquid that you have originally from here. So now from here, you are moving it into another container. So originally it's a mixture of oxygen and nitrogen. And now at 50 degrees Celsius, you can get a pure oxygen over here while leaving the nitrogen in the original beaker. Okay, this is a process of distillation, and we use it to distill a lot of other compounds from a mixture. So say for example, if you have a water and I don't have any other example. Say for example, ethanol. Okay, so ethanol is very light. Okay, so if you have from water and ethanol mixed together in here, and then you distill it. Okay, so ethanol has a lower boiling point, so it boils faster than water. So what will happen is ethanol will move up here as a gas. It forms a gas, moves up here, and then it cools down in the condenser, becomes a liquid again. Then you can collect ethanol in this beaker. Okay, now you are separating it. So distillation is a process of separating two entities from a mixture. Okay, so this is what this factory does, and then what it does, it separates. If I'm not mistaken, this one is a nitrogen, hydrogen tank. This one is oxygen or nitrogen, something like that. Okay, we need to watch the video to really kind of like understand the process involved. Okay, but that's the brief general idea. Okay, so now let's look at some examples of the component of air. So the first one that we're going to look at is oxygen or O2 gas. Oxygen, just simple question. You don't need to answer. Okay, you need to remember whether is it an atom, is it a molecule, a compound, or a mixture. Okay, now we just go back. So this is how I'm going to try and style my lecture for you guys to keep on recalling what are the things that you have learned. Okay, so in this case, of course, it is a molecule because we are talking about oxygen gas. If you're just talking about oxygen as in an element oxygen, then it is an atom. Okay, is it a compound? Yes, it is also a compound because it contains two or more atoms. Oops, my battery is okay. And is it a mixture? No, it's not a mixture because if it's pure, then it's not a mixture. But if it's not pure, then it is a mixture. Okay. So now we have a properties of oxygen here. So this is just a brief properties, just to introduce to you guys. There's no need to memorize, okay, because you can simply wiki and find the information. So allotropes, what it means by allotropes is it's the same element, but it has a different structures. Okay, so say for example, oxygen, O2 is the oxygen that we breathe in, but you can also form an O3, which is an ozone. Okay, remember when you learned long time ago, our Earth has a layer of ozone. Okay, so ozone, the ozone layer is made up of O3 molecule. So instead of O2, it has an O3 molecule. So there is an equilibrium. If you go in very detail about ozone layer, there is an equilibrium between oxygen gas and ozone layer, and how ozone layer is being degraded by all the other molecules. Okay, that we are not gonna go there. Okay, simple appearance of oxygen or even an ozone. It's a gas. It's colorless. You cannot see anything, and of course, it's odorless. So you cannot smell it. In a liquid form, so if you cool down, so what we have here is oxygen at room temperature, okay, at about 25 degrees Celsius, and in my room it's 29 degrees Celsius. But generally, when we're talking about room temperature, it's about 25 degrees Celsius. Okay, so if you cool it down from 25 or 29 degrees Celsius down to this, okay, negative 183 degrees Celsius, the oxygen now will become a liquid. Okay, so if you go down, if you cool it down even lower to minus 219 degrees Celsius, you can form something like this. So a jelly-like substance. So jelly-like meaning that it's a mix between a liquid and a solid, and the color is surprisingly blue. Okay, so our oxygen, even though there's no color, but if you cool it down, when it forms a liquid or gas, then it becomes blue. Okay, and the standard atomic weight of an oxygen is roughly 15.99903. Well, this one is standard, so it's not rough. This is the accurate value of an oxygen. And of course, oxygen, if you go in very deep, you can have slightly different numbers or slightly different weight. The second weight can be 15.99977. Okay, it's very close to one another. So that's why normally when we talk about oxygen, so oxygen straight away, we normally consider it as 16 instead of 15.999. Okay. All right. So what are the uses of oxygen? Again, this is very brief. Oxygen is being used, or according to this data that I found a market analysis report back in 2018, of course, before COVID. Okay, so the market cap is about 450 billion US dollars, and mostly the oxygen are being consumed in these four markets or industries: food and beverages. We have metal fabrication, manufacturing. Roughly about, but the numbers are probably no longer accurate. Okay, in chemical industry and health services. Of course, the health. This one is a very old number. Okay, but nowadays I'm not sure. Probably it goes up to about 30% or so because of COVID-19. Okay, so that is COVID. For example, this is industry, chemical industry. You need to heat up oxygen and ammonia with the presence of palladium catalyst, which is an inorganic material. Okay, you heat it up, and then it forms a nitric acid. Okay, so nitric acid, you can use it for multiple purposes. Okay, and additionally, if you look at this picture on the left-hand side, I'm not sure what that one is. I'm sure it's not welding. It's kind of like using a high temperature to cut metals. No idea what the terminology is, but if you want to burn something other than using lasers, one way to produce a high heat is by burning oxygen. Okay, so that's another example of how oxygen is being used. All right, so let's watch this video. Oops, what happened? Oh my god, sorry, keeps on jumping. Can you guys hear anything?
Steel, one of the most fascinating materials in today's world, and a key enabler of our modern lifestyles. Industrial scale production of steel is closely linked to the availability of industrial gases like oxygen, nitrogen, argon, and hydrogen, delivered in many instances by the Linde Group, a leading global supplier of gases and gas production facilities for the steel industry. Building on the synergies between our gases and engineering divisions, we've gathered vast experience and have developed the Linux concept. This stands for the design and delivery of turnkey, modular, easy-to-install air separation units, especially for the steel industry. Customers can depend not only on a reliable, secure supply of gases, but also on our leading application technologies and expertise. Up to 10% oxygen enrichment decreases fuel costs and improves productivity. In collaboration with our partner, we optimize electric arc furnace operations. Besides decarbonisation, industrial gases offer a host of other process benefits. For both small and large-scale ladles and tun dishes, we deliver the most efficient and environmentally friendly preheating solutions based on oxy-fuel. When it comes to slab reheating, our Linda Reebox solutions offer vast optimization potential at a low investment cost. Our experienced team of engineers ensures that we keep our promises, implementing our solutions hand in hand with our customers on site. Our inert gases help to reduce cycle times in the heat treatment process, ensuring that coils are as bright as expected by customers. Looking beyond these examples, there are many more points in your steel plant where we can contribute to your success. And our research centre is continuously exploring new application opportunities for industrial gases in the steel industry of the future. Backed by our regional and global operation centres, we ensure you get the gases you need in the quantities you need them and when you need them, every time. And if you should run into a problem, our experts are always on hand with a wealth of experience and know-how. We can proudly say that steel is at the heart of our business. Daily, we produce more than 50,000 tonnes of gas for the steel industry worldwide. Our passion, technological excellence, and long-lasting experience have made us the #1 supplier of gases to the steel industry. Most of the leading steel suppliers worldwide trust in Linda. Let's talk about how we can help you.
Okay, so basically that's one example of how this company utilizes oxygen gas to kind of like streamline their processes, producing a better steel and whatnot. Okay. All right. So the next one we're gonna look at nitrogen gas. So again, simple question: is it an atom, molecule, compound, or mixture? You pick your poison. Okay. Is there any allotropes? The answer is no. Okay. There's no allotrope for nitrogen. It's always N2. If you form a different structure, then normally the name changes. Okay. Appearance, colorless gas, liquid or solid. If you cool it down, it becomes white. Okay. Appearance, that one. Standard atomic unit is 14.006, and melting point and boiling point is this number. So what are the differences between, you might wonder what melting point and boiling point. So melting point, so if you are thinking about the concepts of physics or particle of matter, okay. So first off, you have solid, and then you have liquid, and then you have gas. Okay, so for a solid to become a liquid, so this is what we call as melting point. And then for a liquid to become gas, this is what we call as boiling point. So what it means here is that for the solid to become a liquid, or for a solid nitrogen to become a liquid nitrogen, this happens at 159.8 degrees Celsius. And for a liquid nitrogen to become a gas nitrogen, it happens at, oh, sorry, that one is melting. So minus 210. This one is 195.8. Okay. So basically, as long as the temperature is higher than minus 195.8, then you will get a gas nitrogen. Okay, unless if the earth cools down until 190 or 200 degrees Celsius, then you might see liquid nitrogen. But otherwise, nitrogen in our nature or in our current temperature will always be a gas. Okay, so some of the uses of nitrogen is in tires. So all tires contains nitrogen. Even nowadays, if you go to certain companies do your car services, they kind of like do a promotion whereby they sells a pure nitrogen in your tires, because again, when you use a compressed air, a normal air, when you fill in your tires in any fuel station, so the compressed air contains oxygen, nitrogen about 78%, and then oxygen about 21%, and then other gases. But these companies kind of try to promote, I had one company try to promote to me once, to kind of like put 100% nitrogen in the tire instead of having a mixture. Why? Because if you look at this, okay, if you just use a normal air pressure, of course you'll get a humidity. So humidity means there's water molecules, you get oxygen and whatnot. So the expansion are different. So in a hot climate, so the tire might go expanded too big, and then it might rupture your tire, for example, even though it doesn't happen, but just an example. But if you have a pure nitrogen molecule, then you can control the properties of your air better. Okay, so that's one example. But of course, the difference are not that big unless if you drive your car like a racing car, then it's a different story. So racing car, normally they use a nitrogen gas or probably even use lighter gases. But in our normal daily life, you don't need to have a pure nitrogen in our car tires or bicycle tires, motorcycle tires and whatnot. Next one, this is the liquid nitrogen produced ice cream. So this one company in Malaysia, I can't remember the name. I haven't had any nitrogen made ice cream so far, but this is one way people tend to promote a nitrogen made ice cream. Okay, so in all chips, crackers, normally when you buy a packet of chips, right? So normally it's very kind of like thick. It's very huge, even though the content is very tiny, right? So so the chemical company, oh sorry, food companies put in nitrogen gas in here, okay, to avoid oxidation of the food. So to avoid food getting bad very quickly, so they put in nitrogen gas. Okay, so that's part of the industry. So nitrogen gas is being used a lot in the industry, and this is kind of like the picture on the right hand side is just a normal natural cycle of nitrogen gas. So this is without the what do you call it, the influence of a human being. Okay, so this is how nitrogen normally cycles in the world. So you have atmospheric nitrogen in the air being taken up in plants, for example. So you have this, it goes from here to here. Okay, you have nitrogen fixing bacteria. So bacteria that can take up nitrogen gas and then produce something else. Okay, so in legume root nodules, for example, we also have nitrogen fixing soil bacteria that takes nitrogen and then forms ammonium, okay, by the process of ammonification. And then we have a different bacteria called nitrifying bacteria that consumes ammonia into nitrates, and then another nitrifying bacteria consumes nitrates producing nitrites. Wait, this one is nitrites forming nitrates, and then nitrates is being absorbed in plants and being used in plants. Okay, so why do we need nitrogen? Because our body is made up of a lot of proteins. You have heard, I'm sure you have heard about proteins. You have protein shakes, protein bars, and so on. Okay, and the content of a protein is, part of it is nitrogen. Okay, so we have a lot of amino acids, we have a lot of proteins, it contains a lot of nitrogen. So you actually consumes the nitrogen in the air technically into your body, and then when you die or when you poop, you are kind of like removing the nitrogen back into the environment, and the cycles continues. Okay, so this is what it means by animals over there. So animals eat the plants, so basically you consume the nitrogen into your body, and then you poop back, or you die and decomposes, you move back, you give back your nitrogen into the environment. Okay. Right. So what are the other gases? One example is carbon dioxide, because this is one of the major gases that as a human being, it's inside your body. Okay. So again, simple question. Go and answer yourself. Some properties, allotropes. There's no allotropes for carbon dioxide. If you change the name, that becomes something else altogether. Okay. So for example, carbon monoxide is a different molecule altogether. It has a different properties altogether. Okay. Appearance is a colorless gas, colorless liquid, or if you cool it down, it becomes white solid. Okay. So of course, liquid is not colorless; it's a clear liquid. Standard atomic weight, we don't have one, because standard atomic weight is the definition that we use for elements. Okay. So when we have a periodic table, then you do have standard atomic weight. But now it's a molecule, therefore we do not have any standard atomic weight, because now we have a carbon and an oxygen. Okay. So therefore you have a molecular mass. So molecular mass of carbon dioxide is about 44.009 gram per mole. And what happened to this? The melting point is about minus 56 degrees Celsius, and the boiling point is about 78. Again, principle between boiling and melting, you have a solid, goes to liquid, and liquid to gas. Okay, so it melts at about this, I think these values are the other way around. Okay, so this one is melting, that one is boiling. Okay, apologies for that. All right. So some of the uses for carbon dioxide, over here we have a carbon dioxide laser. So uses laser to based on carbon dioxide. Over here you have your what do you call it? I like to call it, with my son, I call it eye digit, because of the kind of like when you drink it, the taste or the feel is like something chewing your tongue. Okay, so you have carbonated waters. Okay, that's what we call it, carbonated drinks. For example, Pepsi, Coke, etc. Okay, so a lot of examples. This one, we again more or less the same as that. So you have carbon dioxide laser. You also use carbon dioxide as a fire extinguisher. Okay. Euthanize animals. Okay. Why is the slide not updating? Can you guys still hear me? I hope you can. Testing. Yep. All right, cool. But the slide is not updating. I've already drawn a few things, but unfortunately, it's not updating. I wonder why. Am I? Oh, okay. So go back. Okay. So this one, another uses of carbon dioxide is to euthanize animals. Once you have finished with it, you have finished with experimenting with it. Sometimes you euthanize the mice using carbon dioxide. So that's the human way possible, because what will happen is, as you look at the properties of carbon dioxide, it is there's no smell. Okay, so what will happen is that your body will just feel tired and sleepy, and then you will sleep forever. Okay, so that's one human way to euthanize an animal. All right, so some other gases are a class of gases that we call as a noble gas. So noble gas contains helium, neon, argon, krypton, and xenon. If you look at the periodic table on the group 18 on the most right-hand side, so periodic table is normally like that, right? So noble gas is the one on the most far right-hand side. Okay, so those they are gases and what we call as a noble gas. Okay, it's being used in a lot of industries, in metallurgy. Okay, in light bulbs, for example, if you look at these pictures, are all light bulbs. So if you change the gas in the light bulb, it changes the color or change the properties. It depends on the properties of the gases. So it changes on the color. So lamps, you can have lasers made up from helium laser, neon laser, argon laser. So you produce a different intensity of laser and whatnot. You can have balloons, and of course, for those who plays Command and Conquer, this one is Kirov. I played games before this. Okay, so it's the same thing, or what happened originally. Of course, it's not a noble gas per se. When long time ago, when people built airship like this, they put in hydrogen gas because hydrogen is light. Okay, but what happened? There is a disaster called Hindenburg disaster. If you can Google it and read the information. So what happened was a balloon filled in with hydrogen gas exploded. So that's the picture of it exploded. Now, normally helium gas replaces hydrogen gas in all air balloons. Okay, because hydrogen gas, if you put in a spark or if you put in a heat source, it will explode. Okay, therefore, for those who are working with or if you guys are learning about hydrogen engine, hydrogen fuels, for example, not hydrogen engine, sorry, hydrogen fuels. So it's a basic principle. Hydrogen can explode, or it can produce a lot of heat and energy, while noble gas like this, it doesn't really do anything. And as you can see here, for a bulb to be bright, you need to put energy in. Okay, but these noble gases do not decompose very easily in a normal temperature. Okay, all right. So we've looked at air. Now we can look at the other two components, two simple molecules. The first one is water. Okay, and the second one we looked at ammonia. Okay, so what is water? What makes water molecule water? We've touched a little bit on water molecules, the shape of water molecules, as we've seen on the bottom right-hand side of the notes. Okay, so some basic properties of water. Water consists of one hydrogen oxygen atom and two hydrogen atoms form H2O. Okay, in reality, if you were to take it in 3 dimension, if you turn it around, it's pretty much forms a V shape. Okay, so some of you might wonder, why does carbon dioxide, I've drawn it in linear, and then when we have water, I normally draw it like that. Okay, so if you were to go in very deep, then you know, there's a lot of chemistry principle behind it, but I don't think we need to go in that very deep. The basic principle is just because remember when we have oxygen, so if I were to draw oxygen, like oxygen and water, okay, H2O. So hydrogen contains 1 electrons, right? And then because electron likes to be in pairs, so one of the other electron comes from oxygen. Similarly, for the hydrogen on the right-hand side. So now you have H bonded with O. At the same time, oxygen also needs to have 8 electron valence, so a total of 8 electrons. So you have 2 lone pairs, like that, right? So now, if you count the number, oxygen you have 2, 4, 6, and 8. Okay, and hydrogen also you have 2 and 2. Okay, so now, what happened to these other two? So because electron is a negative charge, right? So when we learn about electrons a little bit in the last 2 weeks lecture, it is shown that electron has a negative charge. Okay, so what happened when you have 2 magnets? For example, I have magnets over here. Okay, so now it attracts, right? But if it has a 2 polar opposite, it doesn't attract at all. Well, similarly, this is the concept for electrons. It likes to be in pairs, but each pair doesn't like to be with another pair. So there's a lot of repulsion between lone pairs of electrons. Okay. So what happened is that in 3 dimension, if I have a okay, so if I have a pen like this, so in 3 dimension, what will happen is that the electrons will want to be as far away as possible from one another. So now you have something like this. imagine my fist over here is the oxygen, okay, and we have two hydrogens over here, one hydrogen and two hydrogen, and to make sure that the electrons are as far away as possible to one another, the angle between these, okay, is 109 degrees. So this is what the 109 means. Can you guys see? I actually show my picture over here. So I hope that you guys are looking at my pictures as well. If you are on your tablet, then I'm sorry, you cannot see what I'm showing you guys, but otherwise it will be something like this. Okay, so if you measure the angle between these pencils or these lone pairs of electrons or these electrons, the angle is about 109 degrees. Okay, so that's why when we draw, I draw it like this because the angle is 109. However, for carbon dioxide, okay, the molecule shares two electrons. So you have one electron here, one from oxygen, two from oxygen, two from carbon. Similarly, on the left-hand side, it's like that. Okay, so it forms kind of like a straight line molecule like that. Okay, so, but of course, this is basic. If you go in very detail, some of what I said just now is inaccurate. It's not the most accurate ones. But for me to talk to you guys about the most accurate ones, then you need to go deep into chemistry, but in a very basic principle, because the electron share is like that, even though it's not like this, in reality, it's actually going up and down here. Okay, but anyhow, so because of the sharing of molecule, it becomes a linear share, while water molecule, because you want to be as far apart as possible, it becomes a shape like this. Okay, so there's a bend like that one. Okay, so moving back to the lecture notes, water molecule are basically electrically neutral. So a pure water does not conduct electricity, or the conductivity is very, 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 very low. Okay, but if you put salt in there, then salt will help to conduct electricity. Okay, in a pure form, it's normally it's kind of like almost neutral or zero. So it is a polar molecule. Okay, because as again we mentioned, we have a delta negative of oxygen and we have a delta positive of hydrogens. Okay, and you form hydrogen bonds between water molecules, and finally the water is the major component of most organisms, or probably all organisms. Okay, so all right. Okay, so this is just an example. In our brain, 83% of it is water, kidney 83, lungs about 85. In our eyes, we have about 95% of water. Our heart, there's about 75%, muscle 75%. In our blood, we have 94% of water. Okay, so we as human, that's why we need to drink a lot of water. And especially when you are speaking, you are kind of like exhaling a lot of water vapor, so you need to drink. Okay. This is another example of percentage of water in our human body as we grow. So as a fetus, in a baby in our mom's stomach, so we are kind of like almost 100% water. At birth, you are about 80%. As an adult, like us now, about 70%. And as we go older and older, it goes down to about 50%. And when we die, then we will be dried of water and be like almost zero. Okay, so the physical and chemical properties of water have permitted living things to appear, to survive, to evolve in this planet, and is also a universal solvent. Okay, water is a universal solvent, meaning that in our environment, it dissolves a lot of things. Okay, so property of water as a universal solvent. So this is a property of water number one. So I put a title there, the case of sodium chloride salt disappearing in water. So sodium chloride is this, a table salt. So if you wonder like how sodium chloride from a white powder, you put it in water, stir it, it disappears, right? So you might wonder about it, you might not wonder about it, it's fine, we're just gonna cover it, okay? So table salt, sodium chloride, and NaCl dissolve in water very, very easily, as you might observe, or even sugar has the same principle. when placed in water, sodium chloride molecules fall apart. So originally it forms like a very tightly packed ions or atoms. So you have sodium atoms, and then you have chloride atoms, then you have sodium atoms, you have chloride atoms, and of course arranged in a three-dimensional shape. So meaning that it goes all the way from the back and forth. Okay, so for example, if this one is sodium, and you have chloride over there, you also have chloride over there. So it must be an alternating sequences. Okay, the sodium over there, chloride over there, sodium over there, and then at the back over here, again, we have chloride, sodium, chloride, sodium. So this is what you see in that. So if you have a microscope, electron microscope, of course, you cannot use a simple microscope. If you look at the white powder, this is how the atoms are arranged. Okay, so this is what makes it white. So when you place it in water, this structure breaks down. Okay, so the molecule falls apart. The positively charged sodium becomes an A plus, binds to oxygen, while the negatively charged chloride attached to hydrogen. So this is hydrogen and oxygen from water. Okay, so this makes a very stable salty water molecule. So you have, say for example, sodium over here. Okay, so you have a lot of oxygen molecule surrounding the sodium. Similarly, at the same time, you have a chloride which has surrounded by hydrogen. Of course, these hydrogen are all hydrogen from water molecules. Okay, so this is what happens. So this property of water allows for transport of nutrients vital to our animals and plants, and so on and so forth. Okay, so this is part of a property of water as a universal solvent. So similar principle happens if you say you take water and then you put water water. If you have sugar or glucose, you put it in water, you stir it, and then the sugar is no longer there. Okay, same principle happens. Tea, for example, if you infuse a tea, same thing happens, but in case of tea, you have a color. You can see a color going through the solution. Therefore, it kind of like tea becomes a brownish color. Okay, so water is kind of like it is not kind of, it is a universal solvent. Okay, so this is basically another like what I have just shown you just now. So that one is a sugar molecule. Okay, sorry, salt, mineral salt, which has this kind of structure. In contact with water, it breaks down, and you have sodium and chloride as a separate molecule. Okay, surrounded by either hydrogen in case of chloride or oxygen in case of sodium. Okay. Now, properties number 2. Properties of water: surface tension, the mystery of floating water striders. So as humans, for example, we cannot walk in water, right? So if you walk in water, then we'll just fall down. So for insects, like water striders, they can float on water. Why does it happen? So this happens because water molecules at the surface holds very, very tightly together, forming an invisible film. Okay, so that's the picture of water strider from a water angle. So you have water level over here. You can see that it is actually kind of like forming when you have a piece of paper and then you push it down, right? So this is what happens for water strider when it pushes down on the surface of water. So you have a lot of water molecules surrounding this area. Okay, and these water molecules, as shown previously, has a lot of hydrogen bonding, and the hydrogen bonding is so strong that because water strider is light, it doesn't really break the surface tension. Okay, so water surface tension can hold the weight that of water strider that normally sink. For example, if you have a paper clip, okay, so if you have a paper clip and then you put it sideways, it can float, but if you put it in a straight manner, normally it will just sink. Of course, again, this depends on the weight versus the surface tension of water itself. Okay, some aquatic insects such as water striders or pond skate rely on surface tension to walk on water. Okay, surface tension is essential for the transfer of energy from wind to water to create waves and so on and so forth. So it involves a lot of principles that you see, and waves are necessary for rapid oxygen infuse in lakes and seas. So without waves, for example, the oxygen exchange. So if you have a straight line of water, for example, like this, okay. So you know that we've covered previously that water, we have, sorry, not water, oxygen. We have a lot of oxygen on atmosphere as a gas, but living aquatic animals, for example, fish, still need oxygen to survive. So how does this oxygen actually goes into water? And part of it is by having a wave. So imagine that's a wave. We have water molecules here, and then you have oxygen over here. So the wave kind of like crumbles onto the air and then takes up a little bit of oxygen into water molecule, into water. Okay. Again, this one is just an example of water strider can walk on water because of surface tension of the water. And this image is very nice. It shows you clearly that the water strider is actually kind of like walks on water. Okay, next one. So the third property of water is cohesion. Okay, so again, the mystery of floating water striders. Cohesion, what does it mean? Cohesion is water molecules tend to stick to one another due to hydrogen bonds among the molecules. So this is cohesion. Previously, we were talking about surface tension. Both have similarities, both are related, but when we're talking about surface tension, we are just looking at the surface of the water. However, when we're talking about cohesion, we are talking about the whole water as a bulk. Okay, so if you have a container containing water, okay, on the surface, we're talking about the surface tension of the water molecule. However, for cohesion, we are talking about every single thing, from the first layer of water until the bottom of the layer, whereby there are always hydrogen bonding between one another. Okay, so water molecules on the surface have much greater attraction for one another than the molecules in the air. This cohesiveness creates a high surface tension at the surface of water. Okay, again, this goes back into the second properties of water. The water molecules at the surface crowd together, producing a strong layer as they are pulled downwards by the attraction of other water molecules beneath them. Okay, so imagine if the attraction force of a water molecule is the same. Okay, so if say, let's say water has an attraction force of about 10. So if you're thinking about water molecule in the middle of here, so there's a lot of there's 300 degrees area by which the attraction between water molecule exists. However, on the surface itself, there is no water molecule on the top of the surface. Therefore, this is what it means by water molecule on the surface have much greater attraction. Okay, so imagine if it's just half. So half you divide by 10, you have 5. But if you have 360, 10 divided by 360, then you have even less forces, okay, even less attraction. So these are cohesiveness property of a water. Okay, and the fourth one, the fourth properties of water is adhesion. Adhesion is talks about the mystery of water molecule that stays on the leaf after a rainfall. So you're thinking when it rains, why doesn't it just fall down? So why did the water molecule stays on the leaf of water? It's because of adhesion. So what does adhesion means? It means water molecule or adhesion of water, of course. Adhesion of water talks about how water molecules stick on the surface of something else. Okay, so it can be on the surface of leaves, it can be on the surface of something else. And if you have a container like a straw, then there is an adhesion inside the straw between your water molecules and your straw. Okay, you can see this property when water stays on the leaf of after rainy days. Most plants have adapted to take advantage of water adhesion it helps the water to move from its roots into the leaves. Okay, so this is another example. I'm not going to go in detail, but one example is this. If you have a narrow tube compared to a wide tube, if you have a wide straw and a narrow straw, you put it into water, okay, you can see that in the narrow straw, the water levels are higher because of adhesion. Okay. Another example of adhesion is, say for example, if you have a glass of water, and then you put in a paper towel, okay, into another empty glass of water, or empty glass. So what you will see is you will get some solution from here moving into this direction. Okay, and it goes against gravity. You are not doing anything. So what happened is that the water molecule get adhered to the tissue, the paper towel, and then it moves bit by bit until finally it transfers to the other side of the glass. Okay. Number 4. And number 5, property of water. Probably this is last one. No, never mind. We'll just stop here because I'm tired of speaking. So we'll just stop here. We will continue about this next week or next 2 weeks. And then we will move into the other examples of simple molecules. Okay, that's all from me. Thank you for your attention and have a good day.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
Bye.
Terima kasih.
Sama.
Thank you, Doctor.
Thank you.
Thank you, Doctor.